Good morning. My name is Brian Young. Today we're going to be going over Module 26.3.11, Motor Controls. Level 3, Module 11 in the NCCER books. Let's take a look at the NCCER book. See what they have to say. Here's 26.3.11, and as always, they have trade terms. Auxiliary contact. An auxiliary contact is an extra contact. It's usually mounted on the outside of a contactor or a motor starter. You'll have 4 main contacts, 3 for the 3-phase motor and 1 as a holding contact. And then outside of the frame, you can snap on aftermarket contacts, and those are the auxiliaries. Contact device that's mechanically connected to a contactor. It can be used to give an electrical signal related to the contactor's position. Dashpot is a solder pot. It's got solder in it. It's a device that provides a time delay by controlling how fast air or liquid is allowed to pass into or from a container through an orifice that's either fixed or variable in diameter. So that's a timing relay. That's a dashpot. Dropout voltage, basically, it's the minimum amount of voltage that'll keep a contactor sealed in, and if you drop below that, it will drop out. Electromechanical relay, these are the types that we're more familiar with. They use electricity to create an electromagnet, and that moves a plunger that closes the contacts, any of a number of switching devices with a set of contacts that are closed by a magnetic effect. And then the IEC, that's the NECA, National Electrical Contractors Association NEMA, National Electrical Manufacturers Association, is in the United States. International Electrotechnical Commission, IEC, is in Europe. Motor control circuit, this is a circuit that carries an electrical signal that directs the performance of a controller or other devices, but does not carry the main power. Pickup voltage, pilot device, seal-in voltage. Seal-in voltage is the amount of voltage needed to close a contact and keep it closed. Usually the pickup voltage is higher than the seal-in voltage. Once it's activated, you usually don't need as much voltage to keep it sealed in. The minimum allowable coil control voltage that will keep an electromechanical device energized. Usually less than the pickup voltage. Minimum allowable coil control voltage that will cause an electromechanical device to energize. Because there's a gap between the plates of the stationary core and the movable core. There's an air gap, and you have to generate enough magnetism in order to draw in that movable core. And then once it's sealed in, it's closer to the stationary core. So it takes less magnetism and thus less voltage in order to keep it sealed in. All right. I don't have any highlights on page 1. That's always a bad thing because there's usually a lot of good information. As relays or contactors, motor starters are generally used in a motor control circuit to amplify a signal. So they might use 120 volts in order to operate the contactor, but the motor can run on 480 volts. It's safer to use 120 volts as the control voltage rather than 480. That's why they do it. So here's electromechanical relays and contactors. Motor starters are still common, although solid state versions with no moving parts or contacts are rapidly finding their way into all types of applications. So those solid state relays have no movable parts, no moving parts. Diodes, triacs, transistors, all of those types of solid state devices, there are no moving parts. Okay. So at the very bottom of page 1, they start talking about the electromechanical relays. And again, That's using voltage and current to create a magnetic field, and that magnetic field pulls in the movable contact. Here on the left-hand side of page 2, further than halfway down the page, or just about halfway down the page, it starts. It says the power relays shown is thus defined as a double pole, double throw, single break relay. So double pole means there are 2 paths for current to go. Double throw means it has two positions that it can be in, almost like a 3-way switch. A 3-way switch is a double throw switch. It can either be connected to one traveler or it can be connected to the other traveler. That's double throw. And then single break means that it's only breaking at one point. And we'll see a drawing or a picture of that, and we'll talk about single break. Here is an example of a single break. It's pivoting from one point, and on the other side, it's movable. So the make and break is only happening on one side. Let me try this again. Okay. Here the make and break is happening on one point. That's why it's single break. There are double break contacts that break on both sides. The whole thing moves and it breaks on both sides. It can take a higher voltage and a higher power rating than the single break contactors. Relay selection criteria. On page 3 on the left-hand side, talks about when energized, the seal-in voltage is the minimum allowable coil voltage, control voltage that will keep the device energized. So that's the seal-in voltage. What do they say? The pickup voltage is the amount of voltage needed to make it operate. The dropout voltage is the voltage at which it will let go. Seal-in voltage is the amount of voltage needed to keep it energized once it has closed, once the contacts are closed. So here are examples of those single break, double break. Here's single pole. There's only one path for voltage and current. That's a single pole. Double pole has 2 paths for current to travel. And here's a 3-pole. It has 3 paths. So there's the 3-pole. Single break only breaks on one point. Double break breaks on both sides. So this is a double pole, single throw, double break. Some contactors actually have 2 positions it can be in. It can be in the upper position or the lower position, and each of those does something. That's double throw. So all of these are examples of double throw. Here's a double pole, double throw, double break. Okay. And earlier we were talking about double pole, double throw, single break, where it just breaks on one side. I have nothing on page 5. Here's a good drawing on page 6. Even though I don't have any highlights, it's a good drawing to see. Here's your common. The common is going up to this contact bar, and the contact bar can be in one of 2 positions. There's a normally closed, which means off the shelf, out of the box, in your hand. This contact is closed. It's normally closed. Off the shelf, out of the box, in your hand, this contact is normally open with respect to the common. So it's designated as normally open. When you energize this contact bar moves, and the normally open contact closes, and the normally closed contact opens. So normally open, normally closed, and the common provides the power. The coil down here is actually what operates the relay, which makes it work. You can have a 12-volt coil or a 120-volt coil or a 480-volt coil. It all depends on what you're using it for. They have interchangeable coils, if you're changing out a coil on a motor starter, make sure that you're replacing one with the same voltage as the one you're taking out. You don't want to put a 120 volt coil in if they're using 240 volt control voltage. It'll burn up very rapidly. Okay, and there's just another example of those parts. I actually have no highlights on pages 8 or 9. Continuation of the discussion. Here's a nice exploded view of a motor controller. Here's the shell, and the contacts are inside here. We can't see them. Here's the exit points for the three phase, A, B, and C, or line 1, or T1, T2, T3. These are the T leads going to the motor. Line 1, line 2, and line 3 would be up here. Here's your coil. That's what makes an electromagnet. When you energize it, it becomes magnetic, and it causes this to move. This whole thing will move. It'll move in an upper direction. So here's a pretty good view of it down here. This is your stationary core. This is the movable core, and it moves towards the magnet. When it does, it'll make contact with this stationary core that's up on top here. Okay, and these are different types. I think this one is a square D. We use a lot of GE. Here are the contacts internal, and you can see that they have the 3 poles for the 3 phases, A, B, and C. And these are the contacts, the movable contacts, that make contact with these stationary contacts. These will come down on top and seal in. Now, these are floating. They're on springs, and they float because it allows it to make a better connection. If they were rigidly connected to this contact bar, they may not line up exactly. You might have arcing and sparking. There may be a problem with them lining up. So they put them on springs. They allow them to float so that they will self-seat. They'll find their equilibrium. And if one side comes down, I'm trying to do this here. If one side comes down and touches the first contact, this spring allows it to roll and touch the other side as well. So that's why they're on springs, so that they can float, they can move around, and they will find their seating. Okay. I have no highlights on page 14, but here's the nameplate. Tells us everything that we need to know about this. Here's your line 1, line 2, line 3. That's the power coming in. And then way down here, we'd have the T leads down below everything. We'd have the T leads. Here it tells us that the coil is 440 to 480 volts. They're telling us this is a 480 volt coil. So we'd take line 1 and line 2 and hook it up across this coil in order to make it work. We could go through push buttons and start, stop, what have you, come back to this and feed this with 480. We would rather see this saying 120 because 120 is a lot safer. But here, it's hard for me to make out. I can't see. It says anything between 200 and 230 volts AC. It can do a 7.5 horsepower motor. 380, 460, 575. You can go up to a 10 horsepower motor, and it says it's 600 volts max. Okay. Over here on page 15, they're showing you schematics of those, the diagrams. And at the very bottom of the right-hand column on page 15, I have this highlight. To protect a motor from overheating, overload relays are employed. The difference between a contactor and a motor starter is a motor starter has to provide overload protection for the motor. You can have a lighting contactor, that's not a motor starter. It has to have some means of protecting the motor from overloads, and then it can be considered a motor controller or motor starter. All right. Here on page 16, they're showing us more schematics. It's showing that the coil voltage sometimes comes off of line 1, line 2 before the contacts. So if you went through a switching device, that 480 volts would cause that coil to energize, and it would close these contacts, and then you'd start the motor, T1, T2, T3. The T leads go to the motor. Line 1, 2, and 3 come in, T1, 2, and 3 go out. They're the T leads. Okay. Here down below that, they're showing, instead of a single pole switch, they're showing a start-stop station where we have a stop button. It's normally closed, a momentary push button, and a start button is a normally open momentary push button. And here's your holding contact, the M contact. It comes off that M motor starter. Okay. All right, I've got nothing over on page 17. Motor heating, page 18. We have quite a few highlights here on page 18. Melting alloy thermal overload relays. It says figure 21 is a typical melting alloy thermal overload relay used with a 3-pole contactor. It comprises a housing with 3 changeable melting alloy heater assemblies, an internal spring-loaded trip mechanism that operates a normally open switch, overload contact, and a reset button. So these are your heaters, 1, 2, and 3. The full current of the motor goes through those 3 heaters, and they are exactly what they sound like. They're a heater. They heat up when you have the presence of current flowing through them. And here's the mechanically tripped spring-loaded overload contact. The normally open switch is down here. I have one more highlight, and then I'm going to look at a picture and explain all of this to you. But the other highlight on page 18 on the right-hand side says, if a different current range is required for an IEC fixed heater overload relay, or its heater must be replaced, the entire overload relay must be changed. The NEMA, the ones we use here, Square D, GE, the heaters are replaceable. You can take the heaters out and put in new heaters. The IEC, International Electrotechnical Commission, those are not replaceable. It's all one sealed unit. If the overloads go bad, if you need a different size overload, you need to change out the entire overload block. Now, this is explaining that melting pot or solder pot thermal heater. This is the heater going across the starter, and all of the current for the motor is going through it, and it becomes warm. And when the right amount of current is flowing, if it's a, let's just say 10 amps, just to make the math easy, it's a 10 amp motor. When 10 amps is flowing through this heater, it doesn't get hot enough to melt the solder inside here. There's solder inside this tube that's holding the axle for the ratcheting wheel. This is a spring-held set of contacts, and they're held by that ratcheting wheel. Now, when the solder is hard and cold, the wheel will not turn. But if it gets above 15% of the running current of the motor, if it's a 1.15 duty cycle, and we get above that, if we get to 11.5 amps or 12 amps, the solder inside of this tube is going to melt, and when it does, it's liquefied. This wheel is free to turn, and when it does, this spring is pushing against these contacts. It'll push it on out, and it'll open these contacts, and it'll disconnect the control voltage to the motor. So the motor will stop. It turns it off. That's how the overloads work. That's how the heaters work. Down at the bottom of page 19, it has a picture of the heater. There's the tube that has the solder in it, and there's your ratcheting wheel. And it goes across this gap, and you screw it in. There's the trip lever that is held in place by the ratcheting wheel when the ratcheting wheel will not turn. When it gets hot enough, the solder melts, the wheel turns, the spring opens the contacts, and the motor stops. That's how we're getting overload protection for that motor. This is an example of an IEC, that International Electrotechnical Council, Technical Council. This is an IEC rated one. It's my understanding that the IEC contactors, motor starters, are smaller, they're lighter, they're cheaper, but they only work about half as long. You'll get 2 million operations out of a NEMA starter. You'll get about 1 million operations out of this IEC starter. But people are going to these IEC frames because they are economically feasible and they're very easy to change out. They're mounted on DIN rail, and if one of them goes bad, you simply take the wires off of it and snap the catch. You pull the catch back, it comes right off the DIN rail. You snap another one in its place, and you're good to go. You hook the wires back up. So you can literally change one out in 2 minutes, 5 minutes. I mean, if you've done that before, if you're good at it, you can go pretty quickly. This is a different type of overload. This heater goes down into a cavern, pardon me, and the heat from this heater will move a bimetallic strip. The bimetallic strip is what it sounds like, 2 pieces of metal soldered or welded together. They expand and contract at different rates. So when you heat them, they'll bend differently. They'll expand differently, and it causes it to move. And when it does, it disconnects the contacts. It'll open them up. With a heater like that, you have to let them cool back off. It might take 30 seconds, might take 45 seconds. You have to cool them off in order to be able to reset the motor if it's an overload. You also need short circuit protection because these overloads do not protect a motor from short circuit. You need to have it on either a motor controller, which is like a circuit breaker, or you need to have it protected by fuses. Okay. Here on page 22 at the top of the right-hand side, they're actually talking about starting current. Starting current can be 6 to 8 times the value of the run current. Now I'm going to share my screen with you. And hopefully I still have my sound, but there. If the run current for a motor is 30 amps, the start current can be 210 amps. It can be 7 times that, 700%. When you start the motor, this start current very quickly, that's supposed to be almost vertical, rises to that 210 amps. And then as the motor turns, this current will come down to the running current of 30 amps. The reason for that is because all motors act like a generator. So, oops. We talked about generators before as being a coil of wire in a magnetic field. that describes a motor pretty good. So where we have this armature, where this coil of wire is spinning inside this magnetic field, we're actually generating a voltage and a current. And lucky for us, that voltage is counter to the voltage that created it, counter electromotive force. So the faster this armature spins, the more counter electromotive force is generated in the motor, and it opposes the incoming voltage and current running the motor, and it brings this down to a nice level at full speed. If it's an 1800 RPM motor and it gets to 1725 RPM, we're at like 30 amps run current. So that's what's happening. Our start current can be 6 to 8 times the run current. Okay. Now, let's go back to our book here. So that's what that's showing us. Here at the bottom of page 22 on the right-hand side.
Mr. Young.
Yes.
Is the 6 to 8 times start current, is that in highlights on page 22?
I think so, yes. It's in the book somewhere. We'll see it. It should be. I don't see a highlight on this page. Let me see.
That's fine. Go ahead, sir.
Page 26. Both NEMA and IEC motor starters use contacts that are designed to withstand high inrush current encountered when motors are started. So here's designed to withstand high inrush currents encountered when motors are started. They weren't telling us the 6 to 8 times. I think that's under motors. This is motor controls, but in the section on motors, I think we learned that the starting current of a squirrel cage motor can be 6 to 8 times.
Yeah, I did cover that one in the last chapter.
Yeah. On the right-hand side of page 22, very bottom of the page, it says that NEMA, that's National Electrical Manufacturers Association, they standardize things like what a 110 volt 15 amp receptacle will look like, what a 110 volt 20 amp receptacle will look like. They set those standards. National Electrical Manufacturers Association. Magnetic contactors, motor starters are selected based on the NEMA sizes, the ratings, and the motor nameplate data, including the NEMA design letter, voltage, horsepower, full load amps, and other data. So all of that data should be on the nameplate of the motor, and you can select your starter based on that information. So here at the top of page 23, even though I don't really have any highlights, they're talking about the product comparison summary, IEC and NEMA. Okay, on the left-hand side, at the bottom of the page, it talks about plugging and jogging. And I want you to know that jogging means inching, including plugging and jogging, inching operations. Okay, so plugging and jogging. Jogging is also referred to as inching. And it's better if you imagine a conveyor belt. If you imagine a conveyor belt, it's easier to understand what they mean by inching. So, well, there's just a lag time between my cursor. Whoa, what happened? Holy moly. I reversed a long time ago and this thing, yeah, there's a heck of a delay in this pen. Anyway, this is whoop, yeah, there's a delay in my pen. That's weird. Anyway. This is a conveyor belt. It's a very poorly drawn conveyor belt because there's something slowing down my computer today. There. And here's a wheel. Well, boy, that's weird. I can't, yeah, man, oh man. I have to just draw it and then walk away. But let's say we wanted to line up a start mark with a hopper. And here's the start mark. All right, well, we don't want to push start because this thing is just going to take off. So we'll jog or we'll inch. So we just bump it. We bump the start button, but we don't allow the maintain or holding contacts to energize or to pull in. So we bump it, bump, 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 bump. We okay, there, it's lined up. Okay, that's where we wanted it, right there. So that's where we got the start position. So we're good to go. Now we can start the process and we can push start and everything's going to work out just fine. That's what they mean by inching or jogging. It's just giving a little bit of electricity to the motor just to move that conveyor belt a little bit, just inching. That's what they mean by inching.
Mr. Young, does that mean lightly pressing the button?
Well, pressing it and letting go quickly and not allowing the maintain contacts to energize. We'll see what the maintain contacts are later, but we don't want them to seal in because then the motor would just be running. But we bump it with that, the maintain contact open, and we bump the motor and it'll just move that conveyor a little bit. Okay, so jogging and inching are the same thing. Over here on page 24, I don't have a highlight, but this is a good example of a forward reversing starter. They've got two motor starters or two contactors controlling the same motor with one set of overloads. And these two contactors, one of them, when it's closed, the motor will turn clockwise, and they usually call that forward. And the other, the motor will turn counterclockwise, and they usually call that reverse. So on the drawing, you can see that when the forward contacts are closed, line 1 goes to T1, line 2 goes to T2, and line 3 goes to T3. When the reverse contactor is closed, line 1 is actually going to T3. Line 2 is going to T2, and line 3 is going to T1. So they've changed it from 1, 2, 3 to 3, 2, 1. They changed. What happened? All right. They changed the orientation of that motor. 1, 2, 3, 3, 2, 1. Changing any two leads of a three-phase motor will change the direction of rotation. And that's what they're getting at. Okay. Over here on page 25, left-hand side says the total excessive current required for intermittent power demands can be approximated by multiplying the motor full load current by the motor service factor. And that's what we were talking about before. The service factor might be 1.15. You can actually overclock that motor. You can get 1.15 out of that motor. So if it's a 10 horsepower motor, you can get 11.5 horsepower without causing any detrimental damage to the motor. For short periods of time, you don't want to do that forever, but it says if the service factor had been 1.25, then the adjustment would be equal to 16.25 amps. It's 13 amps is what they were saying was the running current at full load, and they're multiplying it times the service factor, 1.25. And they're saying you can actually put 16.25 amps on that motor without hurting it as a service factor. Most service factors are 1.15. Some motors are 1.25. Any service factor adjustment determined that is greater than the full load current permits the overload relay to allow any excessive intermittent power demands without nuisance tripping. So that way, if the motor is crushing rock or something like that, and it's going to be under load, under stress momentarily, you can allow it to go up to 25% over, and it won't trip the overload relay. I don't have anything on page 26, table 6. This is just different size NEMA starters, and it gives you some characteristics of each. Here on page 28, they're showing an IEC starter. Here's a nameplate rating of a motor, 3-phase motor. It's telling you the voltage is 230, amps are 13 amps. 1740 RPM, it's a 5 horsepower. So they're giving you a lot of information on here. 3-phase, okay. The NEMA code is H. Gives you wiring diagrams here for low voltage, high voltage. So really, the volts, they should have had 2 volts listed here. They should have had 230 and 460. And they should have said 13 amps and 7.5 amps, or 6.5 amps. It would be half of that. But this is what the IEC starters look like. Again, the overloads are sealed. It's a complete unit. It's a block. And if the overload, if the heaters go bad, or if you need to change the heater size for any reason because you're changing the size of the motor, you have to change out the whole overload block. If the overload block isn't bad, you don't have to throw it away. You can take it out, store it somewhere, and you can put a new one in to adjust for that new motor. But they do have to be changed. The entire block has to be changed out. You can't get inside here. You can't change out just the heaters. On page 28, very bottom of the left-hand side, it says IEC contactor motor starter selection is based on the percent that jogging and plugging is of the non-jogging and plugging condition. So here's table 7 on the right-hand side of page 28, and I have an AC4. That's the category. The typical application is a squirrel cage motor starting, plugging, and jogging. You'd want an AC4 motor starter. That's that IEC designation. Okay. And they do have some crossover charts that tell you if it's this size NEMA, it would be this size IEC. Here on page 29, on the right-hand side, I have I have one bullet highlighted here. Transient suppression module. These are contactor motor starter accessories, things that you can get. You can get a power pole adder kit, timer attachment, fuse kit, and here's the transient suppression module. So it suppresses transient voltages. Side-mounted transient suppression modules are available to reduce transient voltages and contact arcing and coil control circuits when the circuits are opened. This eliminates electrical noise that interferes with operation of nearby electronic circuits. This is my highlight. It says most modules consist of an RC circuit that is designed to suppress coil voltage transients to approximately 200% of peak coil supply voltage. So those transient voltages will be suppressed to 200% of peak coil supply voltage. So if the coil supply voltage is 120, it will keep those transients below 240. Okay, that's it for this section. Yes, any questions? Okay, on page 32, again, they have more trade terms. You should go in and read those trade terms. They're very good. They give you a lot of information. On the right-hand side of page 32, first paragraph, it says, pilot devices are used to provide sequencing and automatic operation within certain parameters. So pilot devices can be push buttons. They can be timers. They can be proximity switches or temperature switches or level switches, float switches if you're talking about fluids, anything like that. Those are pilot devices that will aid in the controlling of an operation. I was saying to someone that you can make a control circuit as simple or as complicated as you want. If you hook up a single pole switch to turn on a light, that is the basics of motor control. You turn on that switch, the light comes on. You turn off the switch, the light goes out. That's giving you control over that load. Motor controls can be as complicated as having an entire process that starts with the push of a button. And everything along the entire line, the example I think I gave was a 96-ounce bottling line that they put in down at Tropicana, Bradenton, the orange juice plant. They put in a 96-ounce line, and it would take BBs of plastic and extrude it in an extrusion mold, make the bottle, wash out the bottle, sterilize the bottle, put a label on it, fill it with orange juice, put the cap on it, put 6 of them in a cardboard case, and glue the lid shut. Human hands never came into contact with those bottles. Those bottles were made at the very beginning in the extrusion mold. And they went through the entire process without interaction of a human being. It's amazing to think that they had bottles in a cardboard box, and the first person to ever touch them is the stock boy at Publix who takes them out of the case and puts them up on the shelf. He's the first person to ever touch that bottle since its inception. That whole process, you have to start the last thing first. When you push the start button, if you try to start sending bottles down the line before the labeler was ready, you're going to have bottles without labels, and you're going to have bottles without orange juice in them, and you're going to have bottles without caps on them. You have to start the very last process first. So the last process of the cardboard boxes being taped or glued shut, that starts to happen. And then the next part of the full orange juice bottles that are already capped, moving towards the cardboard boxes, that starts to happen. And then the caps are being put on, and then the bottles are being filled, and then the labels are being put on. And, then you get back to the extruder where you're actually making the bottles. It is a domino effect. When you push the start button, the last thing in the sequence starts first so that you don't have any bottlenecks. So it took about maybe 30 seconds from end to end for this thing to start up, but everything would start at its time, and then you'd get to where you were making, and they would just leave it running for 6 hours, 12 hours, and they're just cranking it. They're just cranking out cases of 96-ounce bottles of orange juice. Okay, so here's a transformer with a fuse holder. That's for primary protection, and they can even have a fuse here for secondary protection. These are called control transformers. Control transformers usually try to have an output of 120 volts, but here it's saying that they've got this connected for 24 volt to 24 volt, or 240 volt to 24 volt operation. They're actually using this to step the voltage down to 24 volts on the secondary. And of course, because they've got 240 coming in, they're hooking these up in parallel. Series add voltage, parallel add current. So when they're hooked up in parallel, you can have 240 volts coming in, and each coil is getting 240 volts. When you have 480, you're going to hook them in series, and each coil will still only see 240 volts because they're in series. Series add voltage. So 240 plus 240, you've got a 480 volt input. You're still going to get your 24 volt output, your secondary on that transformer. Over on page 34, at the very bottom of the page, down here, step 2. It says, after the factors have been determined, the proper transformer can be selected by following the procedure normally given in the control transformer manufacturer's catalog application bulletin. And here they're talking about what you do in step 1. You find the inrush current. It says, using table 9, select a proper secondary voltage column to use. If the primary voltage is stable and does not vary more than 5% from nominal, use the 90% secondary voltage column of the table. If the primary voltage varies between 5 and 10% of normal, use the 95% secondary voltage column. So, and it said voltage column up here on the right-hand side. So here's page 35. This is that table 9 that they were talking about. And they're saying that if it's stable, use the 90% secondary voltage. If it fluctuates between 5 and 10% of normal, then you're going to want to use this 95% secondary voltage. So if you have a transformer volt amp rating of 300 volt amps, the 95% secondary voltage might have an inrush of 1900 volt amps. Okay, it's inrush volt amps at 20% power factor, 1900 volt amps. That's how you use that table. I have nothing on page 36, but it has some good diagrams here of different types of buttons. This is a mushroom head button. This is usually an emergency stop will be a mushroom head. It's very big, it sticks out, and it's very easy to get to and push in the case of an emergency. Okay. Single circuit that's normally open, normally closed. Usually your starts are normally open, your stops are normally closed. This is a double pole circuit, or double throw, I should say, because it's double break, double pole. I'm sorry, double throw. This is single pole, double throw. When you push this push button, you have 2 sets of contacts. The normally closed set opens, the normally open set closes. Okay. All right. And here's a typical start-stop station over on page 37. There's your stop is normally closed, your start is normally open, and it goes to the control relay with a holding contact on the control relay. Okay. Well, I don't have much here on pages 38 or 39. This is a logic table. Basically, it's telling you inputs A1 and A2. When we're in the J position, A1 is energized, and when we put it in the K position, A2 is energized. So the contact is closed when it's an X. So A1 is on top, A2 is on the bottom. When it's in the J position, A1 is closed. When it's in the K position, A2 is closed. What they're getting at. Okay. These are different types of switches. Well, that's a pilot light. This is a push to test pilot light. This is a joystick, and it's actually 4-position. If you've ever played the crane game with you put the money in and try to get the stuffed animals, you've seen an example of that joystick. Okay. Over on page 41, they're talking about a temperature switch. This is the schematic for a normally closed temperature switch. It opens on temperature rise. Higher temperature, the switch or alarm. So that's a normally closed. We know it's a normally closed because the contact bar is on top of the node. Normally open, the contact bar is below the node. As it heats up, it would close that set of contacts. As this one heats up, it opens the set of contacts. On page 43, here's an example of a pressure switch. And the way I was taught is that you imagine one of those old-fashioned oil cans that are curved on the top and flat on the bottom, and you push on them and you get oil out. You have to put pressure on the bottom. So that's a pressure switch. This is a normally closed pressure switch. Again, the contact bar is on top of the node. That's normally closed. It opens on pressure rise. This one's not highlighted, but this is it's a limit switch, meaning that something's going to come down a conveyor or it's going to move, and when it hits this switch, it's going to close that switch. Okay. And I don't know, I don't like their drawing here. There you go. That's what I would have. Oh, this is held closed. Okay. Here's normally open, held, or this is normally closed. Here's normally open, held closed, normally closed, held open. That's the limit switches. Lever action, limit switch. So you've got different travel, and it does different things. Okay. I got no highlights on those pages. Here's a highlight on page 48. They're talking about a float switch, and the circle is a float. And again, that's normally closed because the contact bar is on top of the node. The float switch, normally open, the contact bar is below the node. There's a lot of good information in here. I don't want to just rush through this and have you think that there's no good information. I just want to show you the critical content, as they call it. These are proximity sensors. They use inductance, a lot of them, so that if something metallic gets close to them, they can read it and they know that it's there. Down here on page 51, right-hand side, bottom of the page, it says a proximity sensor can be either a load-powered sensor or a line-powered sensor. Load-power sensors are two-wire sensors excluding the ground that are connected in series with the controlled load. They draw their operating current, also commonly called the leakage or residual current, through the load. So load-powered sensors get their power through the load. And over here on page 52, it's talking about the line-powered proximity sensors. Line-powered proximity sensors are three-wired sensors, excluding the ground, that derive their power from the power lines, not the load. So they're line-powered. They're powered all the time, regardless of the state of the load. The load-powered is only working through the load. On page 55, okay, retroreflective. This is a photo or it's a photo switch or a photo detector. They use them in conveyor systems a lot of times. And there are several different types. We kind of need to be familiar with them. Retroreflective I have highlighted, but the direct scan, the transmitter and receiver are separate assemblies located opposite each other on either side of a conveyor belt. Light beam from the transmitter is aimed directly at the receiver. The target to be detected passes between them, interrupting the light beam. That's direct scan. Retroreflective, the other one, you have to take power to both sides of the conveyor. This one, you only have to take power to one side because both the sending unit and the receiver are in the same device. Retroreflective scan, the light beam transmitted from the transmitter is reflected to the receiver by means of a reflector located opposite the sensor. The target to be detected passes between the sensor and the reflector, interrupting the light beam. But the sending unit and the receiver are mounted on one side of the conveyor, so you only have to power up one side. The other side is just a reflective, a reflector. Okay. Polarized scans, they're kind of clever. It has a prism instead of a reflector so that the light comes out and it's oriented either horizontal or vertical. Let's say it's vertical and it comes out. When it hits that prism, it bounces back and it changes the polarity to a horizontal bias. That way, if something shiny does go by, if a metal box goes by, it doesn't reflect the beam back to the receiver and fool the receiver into thinking nothing's there. It doesn't change the orientation of the beam. The polarized reflector or prism does. So it knows that there's something there. Okay. Diffusion scan, convergence scan. You can read those if you want. Here, I think, is the last section, I think. Yeah, maybe not. It doesn't matter. But here on page 57, installation considerations. Over on the right-hand side of page 57, general purpose, NEMA, National Electrical Manufacturers Association. Type 1, a general purpose box, type 1 box is for indoor use. A NEMA type 1 enclosure serves as protection against dust, light, and indirect splashing. They're not meant for outdoor use. You need a NEMA 3 if you're going to put it outdoors. Here's dust tight, rain tight, NEMA type 3. So type 3 is for outdoors. And if it's for heavy rain, it has to be a type 3R, just so you know. Okay. Page 58, they're showing different enclosures that you can use in the weather. There's IEC enclosures. Again, NEMA and IEC both have their own ratings. Here's a good one. We got to take a look at this figure 69 on page 60. It's a schematic and we need to know how to read it. We need to know how to follow it. So here's a limit switch. This limit switch is ZS108A. That's a limit switch. And the wires coming from ZS108A are contained in cable C108H. C108J goes on to limit switch ZS108B. So H or J. C108H is the multi-conductor cable that goes to ZS108A limit switch. And we can see it's numbers 1E, and 1, no, I'm sorry, just 1 and 1E. Those are coming from this trunk line. And here's 1, and here's 1E. And those two are going up to limit switch ZS108A. Now here's another multi-conductor cable. Down here, C108B. And C108B is going to this hand station 108. So this is usually it's manual or automatic, handoff automatic. They're saying LOA, okay? And this hand station 108 is being served by 1A, 2, 3, and 10. We can see those coming down 1A, 2, 3, and 10 in this cable C108B. There's 1A going to the stop button. There's 3 going to the start button. There's 10 going to one side of this handoff automatic, and 2 is going to the normally closed of the handoff automatic. These other wires are internal. 1F, that's a little jumper. This 2 is jumping down to the start button. Okay. Here's our logic circuits. These are fun. we used to take a lot of time in learning these and making sure that everyone understood them. Basically, you have operators, and, or, and is like multiplication, or is like addition. What I mean by that is, this is an example of an AND circuit. So if I have if I have A and B push buttons, I have to close both A and B in order for this control relay to work. So here's my logic table. It's showing that if A is open and B is open, there's no output. If A is open but B is closed, there's still no output because they're in series. If A is closed and B is open, there's still no output. You have to have A and B in order to have an output Y. Okay, so that's the logic table for this AND circuit. And this is a designation for it. Way down at the bottom, they have what's called a NAND. And the only way to explain a NAND is to let you know that the N stands for not AND. In other words, the AND circuit that we were just looking at has the outputs on their logic table of 0, 0, 0, 1. Open, 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 closed. They have an output. Well, this one has just the opposite. Closed, 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 open. 1, 1, 1, 0. Because what they did was they took an AND circuit and the output was put through an inverter. So if you have an input, you don't have an output. And if you don't have an input, you do have an output. So here's my NAND circuit. I have a normally closed contact here from the control relay going to the output. So you can see that if I have A but not B, I still have an output. If I have B but not A, I still have an output. If I have neither A nor B, I still have an output. The only time I don't have an output is when I have both A and B inputs, and that opens this normally closed contact, turning off the output. And here's my logic table. If I don't push A or B, I have an output. If I only push B, not A, I have an output. If I push A and not B, I have an output. Only when I push both A and B, I don't have an output. So they call it NAND. It's not AND. If you have questions about that, I'm happy to go over that in more detail. Just let me know. Okay. I think we're coming down to the end of it here. Here are some functions. Here they're talking about these two stops. If you have more than one stop, they have to be in series because either one of them that you push, you want it to stop the current or the voltage. So you put them in series. So your stops are in series, your starts are in parallel. So that either one of these normally open start buttons, you can push either one and get your output and get the M contactor to energize. So they're saying that this is an AND function and this is an OR function. Okay. All right. And I have nothing on 60 or 69. Here we are on page 71. They're talking about the National Electrical Code rules and regulations, mandatory. Here for motor controller contactors, the motor controller has to be within sight of the motor and of the contactor. NEC Article 430 Part 7 tells us they're used to start and stop motors. Controllers other than inverse time circuit breakers and molded case switches shall have a horsepower rating at the application voltage not lower than the horsepower rating of the motor per NEC section 430-83A1. So they have to be rated in horsepower, and it has to have a rating at least that of the motor nameplate. Okay. Way down at the bottom of page 73, they have an example of electrical interlocks. And I want to explain what we have here. Electrical interlocks make sure that no two things happen at the same time. So here's a normally closed contact from M2, the drain pump, in series with the fill pump, M1. So if you're draining the tank, this normally closed contact is open and there's no way to energize the fill pump. You don't want to be filling and draining at the same time because you're not going to get anywhere. So when the drain pump is on, the fill pump cannot be energized because of that normally closed contact. When the fill pump is on and you're filling the tank, this normally closed contact M1 is open, not allowing you to start the drain pump. So you can only run either the fill pump or the drain pump at a time. But they may ask you something about that. What's the M1 contact in line 4? What is its purpose? To make sure that the drain pump is not energized when the fill pump is operating. You can only do one or the other. You can't do them both. Those are called electrical interlocks. Okay, that concludes 26.311 motor controls. I'm gonna come back to my other screen here. So, do you have any questions?
No, that was a good overview. Thank you.
Okay, very good. This concludes the 26.311 review for NCCER. I hope you found it useful. As always, work safe, work smart, and use your PPE. Thank you.